Hi everyone, welcome back to Dave's Math channel. This is my next video on my daily math problems, which I feature every few days on the Facebook group Classical Mathematics. This is the last one I posted, and it concerns Aliquot sequences. So anyway, let's begin. Yeah, on this slide, before I begin, I think I should point out what this slide's showing here. This is the aliquot sequence starting with the number 138, and I'll get into this later in the video. Anyway, now we can begin. So here, yeah, first I have to state the problem, and before I do that, I think I have to give you a little background on aliquot sequences, what they are. You guys may be familiar with them already, but in case you're not, I'll just read to you what this says. So, the aliquot sum, which is usually known as S of n, of a positive integer n, is the sum of all its non-trivial divisors, i.e. the sum of its divisors other than n itself. So we don't count the number itself. And then the aliquot sequence of n is just a sequence you get where you start with n, and then you take s of n, and then s of s of n, and then s of s of s of n, and so on. In other words, every term in your sequence is the aliquot sum of the previous one. And these have been studied for really, really long time. As a matter of fact, even the ancient people studied aliquot sequences and led to things like perfect numbers and amicable pairs and amicable chains. I'm not going to get into that in this video, but there's been a lot of research on aliquot sequences and aliquot sums. And most of the time they terminate. Most of the time they go to 1, at least for most of the known aliquot sequences. Like I said, some of them can end in cycles, some of them end in perfect numbers, some of them end in amicable pairs or amicable chains. Those are just cycles of length greater than 2, but those are pretty rare. Um, and anyway, so that's just a little overview what aliquot sequences are. And now what the problem is asking for is to find the aliquot sequence of n, where n is up to 200. So n is an arbitrary integer from 1 to 200. We want to find the value n that has the longest aliquot sequence that ends in 1. There are a few that don't. But of all the ones that end in 1, I want you to find the longest one, or n is up to 200. And I also want you to find the largest member of this aliquot sequence. And this is a kind of problem like most of the last few I've been giving, where it's really best to do a brute force computer search. Because otherwise, I mean, if you did this by hand, you'd be going nuts. You'd probably be spending months doing this, which I think a lot of people did in ancient times and in medieval times. And probably right up until the time in which we had computers. There was no good method for computing aliquot sequences other than just grinding them out. Thankfully, now we have computers for that. Um, but anyway, here's my code I wrote to calculate the aliquot. This code just tells, yeah, this calculates the aliquot sequence of a given number n. So you have to give it n as an input, and it's pretty easy to write code to do this. I mean, all it's doing is looping over n going up to something I'm calling n max, and n max is going to be 200. Um, or actually, this just tells you, yeah, this just tells the aliquot sequence of a given number. Yeah, sorry about that. So what we do is we just calculate first the aliquot sum of n, which is just in Mathematica you write the sum of all the divisors of n is given by a function called divisor sigma, and it specifically is divisor sigma of 1 comma n. Mathematicians usually write that with the Greek letter sigma. Looks a little like an O. Sigma sub 1 of n. It's just the sum of all divisors of n, but that includes n. So we also have to subtract n when we're done. So that's what this is doing. It's calculating divisor sigma of n minus n, but we're starting with the given value of n, but then we keep updating that value. So I think I'm calling it S1 here. So S1 is just a divisor sigma of n, and then once we calculate it, we check to see whether it goes to 1. If it goes to 1, we terminate. Or if it goes back to a previous value, that's why I'm using S1. We have to store previous values. If it goes back to a previous value, then we terminate as well. That means we went into a cycle. And I'm weeding out these possibilities when we go into a cycle. I'm making sure that it ends in 1. And if it ends in 1, the other thing I do is I keep track of the maximum value of S as I'm going through this loop, and then the thing will output that value. Actually, I don't think this doesn't compute the maximum value. Does it? Let me look. Um, well, it computes a table, and we can always find the maximum value of a table. So it outputs the whole table, the whole Aliquot sequence of n. Anyway, and it's not hard to do. That's what this function does, and uh, and then I did it for all the values of n going from 1 to 200, and in this table I show here, I left out the values of n going from 1 to 100. Most of those aren't very long. I think the longest Aliquot sequence with n less than 100 is probably the one for, I'm not sure, I think it's 30, which has like length 15. And I think its largest element is 259, so it doesn't even get that big. But they get bigger as n gets larger, and I think you can see just from looking at this table what the value of n is that gives you the longest Aliquot sequence. That's for n equals 138. The length of that one is 178. I don't know how easily you can see the numbers in this table, but so in the first column I've got n, and the second column I've got the length of the Aliquot sequence. Most of them are pretty short. And the third column I've got the maximum element, which you can just use in mathematics. You just do max of a list. And it turns out that the maximum element for n equals 138, you also get for n equals 150 and 168. And the reason for that is because 150 and 168 occur early in the Aliquot sequence of 138. I think 150 is just the next. That's the Aliquot sum of 138. And then 2 more steps you get to 168. So it's 1 to 38, 150. I can't remember offhand what comes after 150. But the number after that is 168. And that's why the Aliquot sequence for 138 has length 178, but then 150 the length is 177, and 168 is 175. And the largest element is what is it? I can't even read that number. It's in the billions. 100. It's about 179 billion. I can't read it, unfortunately, but it's a very, very large number. And anyway, that's the longest Aliquot sequence you get. And if you want to see it written out in full, here it is. I showed that on the cover slide. This is probably a little bit easier to see, and you can just get it by using the Mathematica function I defined, Aliquot sequence of 138. It's this long table with 178 elements. The largest element is in here somewhere. And there's a lot of other large ones near it. So anyway, that's the Aliquot sequence of 138, and that's the solution to the problem. But before I finish, I think I should just mention one more thing. Like I said, Aliquot sequences have been studied for a really long time, and it's not known whether every Aliquot sequence either terminates or ends in a cycle. And the smallest value n for which the fate of the Aliquot sequence is not known yet is 276, which happens to be twice 138. And this graph is showing the first 2208 terms of the Aliquot sequence of 276, and by the 2208th term, it's already up to about 10 to the 220th power. And it's pretty amazing to me that these Aliquot sequences can even be calculated, because one thing you have to do to calculate the Aliquot sum of a given number, you have to be able to factor that number. And I think this is about the limits of how large we can factor numbers like this. I wasn't even aware. I think you can't even factor general numbers with 220 digits. I think maybe the reason why these are a little bit easier to factor is they have a lot of small prime divisors. But I think that, as far as I know, the largest numbers that can be generally factored have about 150 digits, and the security of RSA, which is the crypto system that guards all your passwords and your financial information and all your credit card information. That relies on RSA. And the fact, they use the product of two primes with about 300 digits, which can't be factored today. Um, but anyway, so this is the Aliquot sequence. The part of it's known up to 200 of 276, and it looks to me, I'm pretty convinced that this thing never terminates. I mean, so I think there are a lot of aliquot sequences that go on forever, although nobody's proved this. I don't even know how you would prove this. Uh, but anyway, I just thought I'd show you this. And this completes my video. So thank you for watching. Long live math, and I'll see you guys next time. Bye.